Thank you, and welcome everyone. I am Fani Dathar. I'm a data science solution architect with Neo4j, and today I'm going to talk about graph data science and relationship-driven AI. I would like to focus on the importance of adding relationships to your existing AI and machine learning pipelines, and also how to get started. What are the, how you are doing today with machine learning, setting up machine learning pipelines, addressing different use cases, and how this is going to be different than what you're already doing today. So this may be a little bit new to folks who are not familiar with networks and graphs, but don't worry, it's going to be a very basic introduction in the beginning, and then we'll get into the details of machine learning and how graphs and how relationships enhance the AI ecosystem in general. Right? So if you think about it, everything is naturally connected, right? From people to processes to different entities that that describe a business or an event or any physical phenomenon, right? So when we look at a business or a company, it is represented, or it can be represented as a network of employees, network of with customers in the same network, suppliers, partners, marketers or influencers, etc., etc. And once you bring in the interactions of customers with that business, then you can think of transaction networks, like how a particular customer has interacted with the business, whether they simply browsed few offerings on the website, or they accessed few items on the website, bought some, looked at some, added some to the cart, and so on and so forth. And we can also think about the entities that describe the business and describe the processes like supply chain management, order systems or payment systems. And we also can also analyze risk management by looking at this network as a whole. And once we start bringing in the semantics that describe the relationships between various entities in this network, then we can even capture the knowledge and make these knowledge networks much more richer by bringing the enterprise content, domain-specific content, ontologies, and any other additional information that we can bring in to enrich our existing understanding of the particular business and so on and so forth. So all the problems that we are dealing with today are very relevant to businesses in terms of how can we make our decision making intelligent, contextual, and so on and so forth. So and that's the goal of relationship-driven AI. When we look at our traditional machine learning models, our machine learning models ignore network structure because it's too difficult to extract from the data sets or the data structures that we use to train our machine learning models, supervised or unsupervised, or any other state-of-the-art machine learning models. So the idea here is to include relationships into machine learning models by using the right data structures to store and retrieve those relationships, and add those relationships to AI and machine learning pipelines to make them contextual and also unlock otherwise unattainable predictions. These are some of the bold statements, but let me explain this by taking an example of recommender system. Right? So when we look at the interactions of people, when customers go and browse Amazon or any other e-commerce website, there are these users. When they log into Amazon, there are these sessions that are created, and these users browse through a bunch of products. Some already know what they are searching for. Some don't really know what they are searching for. They have a faint idea, so they start with some kind of search phrase to see, hey, I'm interested to find, I'm here, I'm on Amazon website to buy some lamps for my porch. Then you look for light bulbs, you look for light fixtures, you look for anything that goes with lamp assembly on the porch, right? But not everybody will be using exactly the same search terms. Not everybody will be using or looking for the exact same light fixtures. So that creates some heterogeneity in terms of how users interact with your business. And when you start mapping this out, the interactions, it naturally falls into a network. Like in this example, we have these purple nodes, which are light bulbs, light fixtures, antique lamp, and then these light bulbs. So these are the actual products. And the magenta nodes or the pink nodes are the session IDs. And we have these orange nodes who are actual users who are browsing this website. Now, given this scenario, Amazon or any other e-commerce system um, would like to create some kind of recommendations so that when a new user comes in to the website, the business wants to recommend some new products, or when an existing user is searching for a light fixture, you may want to also recommend similar items or the items that go with that particular light structure. And to address such problems, recommender systems are pretty common, and you see it everywhere now, and they influence the business, not just the e-commerce business, but any businesses or any other business get really. Uh, Deepti, there is a question asking for captions, and are captions possible here, or just?
I'm sorry, we will not be able to turn on the captions right now.
Okay.
If you could bring in more details, why would you want it? So probably we can work on the background.
All right. Thank you. Thanks. Okay. So going back to this example, if you want to build a recommender system, this is what we are doing today. We are taking the network and then we are converting that rich information that connects different entities in the network that is shown in the previous slide, and converting it to a tabular data. And we are using this tabular data as input for our downstream machine learning models. So this tabular data is basically taking this rich multi-dimensional structure and then flattening it out into rows and columns. And then here we see Mingo or Jane or Aditi, they have purchased one product, but there's no information about that particular person interested or not interested, have purchased or have browsed for some other products. And given the size of the businesses, Amazon has like 8 million products or 120 million products in their portfolio. You can imagine how sparse this data structure becomes, and then any particular user may have only bought like 50 different types of items. They might have browsed 200 different types of items, which is like 0.0001% of the actual product portfolio that Amazon carries. So that's the problem that we are seeing. The problem of sparsity and then high dimensionality of these data structures, which amplify the issues to generate these personalized recommendations. Because our machine learning models require us to have this tabular data matrices, and then the only way we do is to take the real network and then flatten it out. That increases the problem sparse and also insufficient information. Like I said, out of this 20 million portfolio, I have probably browsed like Amazon website 200 times in last 2 years and may have seen like 20 or maybe 100 products at the most. So, and if Amazon wants to recommend some kind of products to me, then they can rely on multiple options like content-based recommendations, collaborative filtering. But for proper collaborative filtering, they do not have any sufficient information about me as a customer to generate any personalized recommendations for me, right? And then for content-based recommendations, they are homogeneous. You could only do word embeddings on the content, or you reduce the dimensionality of the vocabulary by running matrix factorization. And all this gives rise to this macro level insights. And there are other issues like echo chamber effects, cold start problem, insufficient information, and so on and so forth. So the idea of using relationships to preserve the heterogeneity and the high dimensionality of the data that we are capturing is really, really appealing here, because we are losing all that information, even though the relationships are already there in our data sets. So what's the solution for this? We should take advantage of data structures to capture the network structure that we are ignoring, so that we can apply some machine learning models. And we should also take advantage of the graph databases, graph query languages, to store and retrieve relationships between different entities so that we can get different types of insights. And there are a bunch of algorithms in the network world that can be used to generate insights from this networks, real world networks, and also infer new relationships so that we could make use of the additional context that's generated to overcome problems like cold start problem or insufficient information issues and so on and so forth. At Neo4j, we look at every graph, or every graph that's stored in Neo4j as a graph consisting of factual knowledge. And using graph algorithms, we enrich the graph that we build with factual knowledge, with semantics and additional context, so that we make this data structure even richer for addressing a variety of use cases that are otherwise really hard to do today. So relationships, coming back to the point that I started with, relationships enhance all stages of AI and AI landscape. So AI landscape is not just machine learning, right? So AI landscape has all the tools that enable intelligent decision making or data driven, and that is the intelligence is data driven, and then intelligent decision making. So if you think about relationships, the relationships make it possible to capture the data and then capture the knowledge from the information that we gather from the data, and and inferring or derived relationships or semantics from that data. And once we have this foundation, then we can use graph algorithms to generate insights and more knowledge from additional knowledge based on the factual information that we have. And we can also use these connected features, like the features coming from relationships, to enhance our machine learning models. And these, we call them as graphy features, or the process is graph feature engineering. And when you combine graphy features with your existing features in your machine learning models, you can call it as graph enhanced machine learning, or graph supported machine learning, or graph machine learning in short. And once we have all these things in place, then the data structures also allow us to do some investigations, and also the expressive nature of graphs allows us to do some explainability, and allows us to explain the decisions that we make, giving rise to explainable AI when we use relationships. And the most interesting part to me is we could use these graph data structures and relationships to generate these counterfactuals, and then see the effect of what would have happened if I did not use this feature in the machine learning. Was my model has the same predictive ability if I would not have used this feature? That gives rise to explainability again, and also answers a lot of questions around bias in machine learning models or in your decision making systems. And we can always take all of this together, integrate these knowledge graphs with other machine learning models for heuristic AI, and then capitalize on the data, information, and the knowledge that we generate. So relationships and graph data structures are not just some add-on features to your machine learning models, but they enhance all stages of AI, making your AI ecosystem truly intelligent and then evolving and with time. So that's the vision of relationship-driven AI, and I'm going to start talking about graphs from this point onwards, because graphs are the data structures that capture relationships. and the data science aspect of the data science aspect of, uh, of this discussion, where you're using algorithms on graph data structures and then enhancing machine learning models. We call this whole thing as graph data science, which is like the data science that you are already familiar with, which requires some exploration, some data storage, some unsupervised learning, and then visualization of the results and communicating with business stakeholders and so on and so forth. So when you look at these graphs or graph data science applications, you see all these different use cases that are currently very relevant to the market, to the industry, to various businesses, like fraud detection, community, user segmentation, identity disambiguation, personalized recommendations, and in life sciences, anywhere from drug repurposing, drug discovery to medical device management, churn prediction, search relevance, and so on and so forth. Every use case that you see today will be benefited by adding relationships to your AI ecosystems, AI ecosystem, by bringing that additional context that you need. And then the topic, then you might want to ask me now is, this all looks great, this all sounds great. Where do I get started, or how do I get started, right? So at Neo4j, we provide this platform for folks to get started with, started thinking about how to capture the information in the form of a graph, and also how to use graph algorithms to generate those insights, and finally combine the insights with machine learning models. And it's a three-step process. That's what we see in many of our in many instances in our customer landscape when they get started with graphs. The step one is to build the knowledge graph, the foundation, by bringing in the factual knowledge that you see. When I say factual knowledge, is basically the data, and bring it over to a graph, build the data structure. And how do you build the data structure? So these are the building blocks of a knowledge graph. The nodes represent an entity in the graph which describes a certain aspect of your business. Like when people network, an employee is a node in a graph, and that employee has a name, some other PII, and some other social identities or a digital identity like a LinkedIn profile or a Twitter handle, and so on and so forth. So you can represent a person as a node in the network and add metadata to that node to describe that person. And then there are other entities, like there are products that are manufactured or sold by the business. They'll become nodes, and then product has a description, what brand, what model, and so on and so forth. So in this example here, we have two people, Andre and Micah, and Andre drives a car, but Micah owns that car, and Andre loves Micah, and Micah loves Andre, and Andre lives with Micah. So you see the relationships describe much more information about how these different entities are related to each other. And these are the building blocks of a knowledge graph. And we can extend this knowledge graph and then capture as much data as we want and use a query language like Cypher to traverse the graph, find the patterns that we're looking for, and then use that output as the information that you want for your decision making, or the knowledge that you want for your decision making. And we also provide a couple ways to visualize the graphs so that you can explain the results to your business stakeholders. What can you do with a knowledge graph? Now, see that once we have the building blocks, and then you expand the building blocks to capture a lot of heterogeneous entities in your business. Think about life sciences. Life sciences, if you are working in a pharmaceutical company, thinking about how do I manufacture this drug? Drug manufacturing process is not very simple, right? So drug manufacturing means you need to think about what is this drug. Take simple Tylenol, which is very common, right? But Tylenol has something called active pharmaceutical ingredient, the material that makes our headaches go away, followed by the other materials that combine with active pharmaceutical ingredients to make it in the form of a pill. And then And then there is a lot of research has already been done on how a particular drug reacts with a tissue, a gene, and then how a drug is used to treat a disease, and how genes are connected to other genes. And then from the marketing side, how a drug is marketed by which brand, how is it made, and so on and so forth. So this knowledge graph captures a lot of aspects of this and a lot of aspects of this business. And then you can start asking questions like, what completes connections from genes to diseases to targets? Imagine if you're using a relational database and using machine learning, then to answer this particular question, what completes the connections from gene A to disease B to target C, it would have taken a lot of pre-processing of data, and then maybe some kind of an association mining to get to the point. But in a graph, it becomes traversing those relationships and giving you the answers. And as you can see, there are a lot of these trivial questions on this slide that can be answered by simply looking at the relationships in knowledge graph. But otherwise they're really, really difficult if you think about using traditional methodologies. And you can also go as wide as you want. Like when you think about organizational knowledge graph, it's not just describing one particular aspect of the business. Now you want to go as wide as you want by capturing these relationships and ask this question: how a particular ship, the cargo vessel that got stuck in the Suez Canal, is affecting my marketing campaigns in Venezuela or something like that. If you want to understand the effect of how the global supply chains react due to some geopolitical disruptions at in one part of the world affecting the bottom line of a business in the other part of the world, you need to know how they are related to each other, and that's what organizational knowledge graphs are all about. So it's so powerful. It's so amazing when you start thinking about how these things come together, when you start thinking about relationships between entities in your business. And that's just the foundation. Once you have the foundation, then you can use a bunch of graph algorithms. So what are these graph algorithms? You heard of regression, you heard of linear regression, you heard of classification, you heard of clustering, and so on and so forth. But if you think about it, what do you use these clustering algorithms for, and what do these clustering algorithms do, right? So clustering algorithms look at the data and then try to find the relationship between various data points in this multi-dimensional space that you describe these data points using some vector. So in the graph world, entities are connected to each other, but there is no, there is, the, I mean, they do not conform to the Euclidean space. That means the distance between any two entities is not the Euclidean distance that you use in your clustering algorithms. It's a topological distance, like how many hops out two entities are connected to each other. So now the graphs are multidimensional and they do not conform to Euclidean spaces. Then your regular algorithms that you use in your machine learning models do not directly work on the graphs. So you need to have a different set of algorithms to get the insights that you need, and that's what these lists provide. And don't worry about the list of these algorithms. Once you start using it, they're pretty evident. And as you can see, these list of algorithms are grouped into different categories. Like centrality and importance algorithms are, used to ask questions like, what's important in my graph? Which nodes are influential? Which nodes are vulnerable to the effects, like I said, the geopolitical effects that happen in one part of the world? How do I do capacity planning, and so on and so forth? And similarity and pathfinding algorithms are used to find associations between two entities, and clustering algorithms or community detection algorithms are used to group different nodes in a graph. So if you look at the collection of graph algorithms, they are all unsupervised in nature, meaning that you have a graph and then you're using these algorithms to ask this question: I don't know what to ask. You tell me what's there in my graph. And to get to that point, you need graph algorithms on knowledge graph. And then you can take the outputs that you get from this unsupervised learning and feed them to your supervised machine learning side of the things, where you say, given this insight, given this community statistics, can I predict a link between two nodes? Or can I classify this node as one category versus the other? That's where your regular machine learning models come into picture, like logistic regression, neural networks, decision trees. Gradient boosted trees, and so on and so forth. But the inputs to those machine learning models come from the outputs of the connection between that world to the machine learning and the existing AI ecosystem. Um, and what it will do is all this process will result in what we call enriched knowledge graphs. That means your knowledge graph, which is simply a collection of all the data that you are seeing on the left-hand side, is now made even more powerful by taking the outputs of graph algorithms and then inferring new relationships, adding new context, and going back to the cold start problem. If you have a new person or a new customer signed up, you don't know anything about the customer, but you want to throw some recommendations to the customer, so that you want to see like how you want to throw recommendations to the customer to generate to I mean to make it more interesting for the customer, right? So by using these semantics, derived relationships, we can generate the additional knowledge, and that's what we call enriched knowledge graph. And I'm going to go over a few of these examples that we see where it becomes really clear now how these relationships come into picture, and how you can start addressing these use cases that I talked about in the beginning, that they are not really uh, performant or addressable using traditional machine learning methods. So for personalized recommendations, graph data structures or the relationships can be used to capture customer interactions and customer journey using a knowledge graph. So these relationships will also tell you how does a particular customer is engaged with your business, right? So this customer logged in, or a user, not user logged in, looked at a product, clicked on a different product, clicked on a different product, clicked on a different product, added a product to the cart, and then finally purchased a different product. And once you start mapping out these journeys, then you see how people are reacting or interacting with various parts of your website. And it also lets you analyze these customer interactions using graph queries and find the communities of customers, generate these cohorts of customers, so that you want to know something about this group of customers, and further analyze, where are they coming from? Is there any commonality between these kinds of customers? Like, are they more interested in the artistic type of products? Are they more interested in more practical type of products, and things like that? And then you can make these features useful or amenable to your machine learning models by converting the graphy features to vectors using fancy algorithms like node embeddings, and then you can use them as inputs to your machine learning models to generate final product recommendations based on correlations between products, and also taking into advantage how these different products are associated, and the proximity between different entities as inputs to your recommendation models, thereby improving your personalized recommendation system's quality, and also taking care of the sparsity of information that you had to deal with if you wouldn't have had a graph data structure to capture these interactions. Similarly, in identity management, again, capture relationships between entities across data sources. What is identity management? So because of increased number of digital touch points, right? So now it's not every business wants to reduce friction. So earlier, if you want to buy something from a company or from a business, you had to go to their physical store, and physical store locations are not everywhere. So now online purchases, online e-commerce businesses are everywhere now, but then they only had a certain type of interface that you can go to your computer and open the website and then do purchases. But now you can open the websites on your mobiles, and you can purchase products from a certain business not by going to their website, but by going through a third party aggregator website. So the number of digital touch points have increased, and it's only making data even more um, and it's making data even more heterogeneous and making it difficult for the businesses to identify who is this customer. Do I know him already? If I know him already, what are his or her preferences? How can I improve the customer satisfaction by recommending only by recommending products that match this customer's preferences as well as the historical interactions of this customer with the business. To get to the point, you need to know who that particular customer is. And sometimes people log in anonymously, you don't have all the information, there's missing information and so on and so forth. So customer identity resolution is one of the important and one of the hardest problems to solve, which feeds into many downstream applications. Again, relationships and a bunch of graph algorithms in a sequence will help you refine that sample set that you need to look at to resolve a particular customer as a known or an unknown identity, unknown profile. Life sciences, again, we can use graphs and graph algorithms for capturing the events in patient journeys and analyze them for proactive monitoring. This is becoming increasingly interesting for the insurance companies, medical insurance companies, hospitals, and pharmaceutical companies and medical research companies. If you know how a particular patient reacts to a particular type of treatment, a particular type of drugs, particular type of diagnosis, then you want to map out those journeys and see if there is any kind of pattern that we can learn from. And also when a patient is starting out in a certain journey, we can nudge them towards a better outcome and so on and so forth. Again, relationships come there into picture, and if you add relationships to your models, you'll get a better understanding of the scenarios. And when it comes to graph native machine learning, like I said, you can take the graphy features which come from these relationships and add them to your machine learning. Graph queries are simple pattern matches on a graph data structure, where here you're asking a person who is enemy of a person who is also enemy of person is most likely the friend of this person. Like person P1 is a friend of P2 because they both don't like a set of people. So you can infer that person P1 is similar to person P2, and you can use the topological distance between these two people as a feature to group them together and help your classification model learn something about those people. And you can take the outputs of graph algorithms also as scalar values and then add them as features to your machine learning models. And finally, you can generate vectors, which are embeddings of these nodes in a graph, and use them as inputs to your downstream neural networks and so on and so forth. And once you combine these features, graphy features, you can feed them as inputs to your predictive models, and then you have some examples to learn from, and then you can start predicting the labels for the unlabeled examples like node classification, and you can also talk about link prediction. Like if you see two entities that are not currently connected, but because of the environment they are in and the properties combined together, what is the likelihood of a link forming between two entities? And you can use a classification model for that. You can use heuristics for that. Either way, you can create these links between or predict the links between two entities using machine learning models. And you can see that machine learning models enhanced with graphy features have better predictive accuracy than not using connected features or graphy features. And there are few examples and beautiful examples to support that claim that I just said. So to end this talk, I have I hope I convinced you that relationships are really important. and relationships are needed to make your AI ecosystem truly intelligent and also improve the explainability of the decisions that you're making, and also helping out with a lot of other things like addressing those complex use cases, higher order use cases that you wouldn't have had an opportunity to crack with the existing tool set that you have access to. And at Neo4j, we provide this graph data science framework, which is a combination of a database to capture all the data. And graph data science library is a collection of graph algorithms that can be used to generate more context, and Neo4j Bloom as a way to visualize these results and also explain it to your business stakeholders to make sure what makes sense, what doesn't make sense, what do we know, what don't we know, and so on and so forth. So the goal is, we want to help you make better predictions, and then let us know if you want to learn more. And there are so much materials. And then thank you, ODSC folks, to giving us this opportunity to talk about relationship-driven AI. And we are also presenting. We really like the ODSC conferences, because they give us they provide this avenue to interact with upcoming data scientists and also other companies in the data and analytics space, and then have this really good productive discussions on how we can all as a community come together and then make the AI models better and better and so on.